Hello guys, welcome back to Educational Era. Today is the second part of simple harmonic motion and we will be going over finding the equation for velocity, displacement and acceleration of a body moving in simple harmonic motion. So before we move in velocity, displacement and acceleration grind, let's talk about an example of a body, actually of a projection in a circle as a simple harmonic motion. So let me draw a circle real quick. Alright, so here is a circle. And let's say this is x dash and this is y dash, and this is point of origin. Now let's take a radius from point O to point P, that is going to be this, and this angle is going to be theta, right? So let's suppose that this line or radius OP is going to move throughout the circle with a velocity, with a constant angular velocity of omega, and we know that omega is going to be angular displacement by time, so angular displacement is going to be omega t. For now, just keep this in mind, we'll use it later on. So now if you see, let me use another color of paint, so let's make it red. So if you see the projection of the line of the radius OP on x dash, which is going to be this, let's say OD, then the projection keeps on decreasing up till up until when the line OP gets up till here, right? Gets till here. As the angle becomes 90-degree, the projection of the line OP keeps on decreasing. If you want to see it visually, then let's say after a certain interval the line OP gets up till here, and let's see this right here, right? That is our line OP, and if you project it on x dash, then we'll have OD here, right? The length of OD is decreasing, the projection is decreasing, and after OP gets up till here and starts moving in this direction, then the projection again starts to increase, right? You see, let's say OP, the line OP gets up till here, and if you see the projection, then again it's increasing, right? And this cycle repeats itself throughout the complete rotation. So if the line is OP here in this third quadrant, then the projection is again decreasing from here to here onwards, and again it's going to increase from here to here and so on. So can you tell that the projection of OP as the angle increases is good? The projection of OP as the angle increases is an example of simple harmonic motion. Well, you can, because the projection, first of all, the maximum projection, there is a specific maximum projection, and second of all, we have constant angular velocity, which means we have constant frequency, right? Because constant angular velocity would mean that it has constant frequency. So after you know this, we can actually move on to derive the equation for these three. So let's get right into it. All right, so let me again draw the circles. Say that this is our angle theta, and we know that theta is going to be equal to omega t. And I want to let you know that if the projection of line OP on x-axis, that's a simple harmonic, then you should also know that the projection of line OP on y dash is also simple harmonic, because they are the same thing, right? Literally, if you rotate the circle the 90 degrees, then y dash would be here, and it would possess a simple harmonic motion too. The projection would possess a simple harmonic motion too. So let's actually get the equation for displacement, velocity, and acceleration on y dash. So for that, first let's draw a line parallel to OX. So let's draw it from P up till here, right? So let's say these two are parallel. Let's name it OD. So this is our projection on y dash, and let's say up till here the displacement is y, and since this angle is theta, then this angle should also be theta, and let's say the length of OP is r. Now that we have supposed everything that we need, let's see. So sine of this angle is going to be its perpendicular, which is this, by its hypotenuse. So sine theta is equal to OD by OP. Now if you write their respective terms, then sine theta is going to be y over r, right? So then we get that the displacement y is equal to r sine theta. There you go, that is our displacement equation. Now if you take derivative of this displacement equation right here, then you will get the velocity, because dy, small change in the displacement per unit time, is going to be its velocity, right? So let me use another pen color to get the velocity, right? Let's get red, and let's differentiate this equation. So dy dt of y is equal to dy dt of r sine theta. Now we know that theta is equal to omega times t, right? So let me clear this off. All right, we can fit it in here. So v is equals to r dy dt of sine theta, which is going to be derivative of sine theta is cos theta, so cos theta is omega t, times derivative of theta. Derivative of theta is going to be, let me just write it down with another color. Derivative of theta is going to be d theta by dt from here is equal to omega dt by dt. That is our omega. So p is equals to r cos omega t times omega. Then we get velocity is equal to r omega cos omega t. Now we know that we can change cos to sine, right? Because let me do it again, another color, because we know that sine square omega t plus cos square omega t is equal to 1. Then we know cos omega t is equals to under root of 1 minus sine square omega t. Then velocity is going to be r omega 1 minus sine square omega t. If we multiply the inside terms with r, we get omega is equals to a. So sorry about this. Let me erase this and let's get the thing. If we multiply this by r, we get omega under root r square minus r square sine square omega t. And we know that r sine omega t is our displacement, so we get omega is under root r square minus omega square, so sorry, displacement square. Displacement square. All right, too much red here. Let's use another color now. All right, so this is our velocity, hence v is equals to omega under root r square minus y square. Let's take this as equation 2 and this as equation 3. Now if we again differentiate this equation 2 right here, we know that the derivative of velocity per unit time is going to be our acceleration. So if we differentiate this right here, we get dv by dt is equals to d by dt of r omega cos omega t. That is going to be again this is going to be a is equals to r omega d by dt of cos omega t. Now we know that derivative of cos is going to be minus sine, and if we derivative of omega t with respect to t is going to be omega. So I'll just write this down directly. So a is equals to r omega minus derivative of cos sine omega t times derivative of omega t with respect to t is going to be omega. Then let's move this here. A is equals to minus omega square r sine omega t, and we know this a again is our displacement, so therefore a is equals to minus omega square y. There you go. Those are all the 3 equations for displacement, velocity, and acceleration. Let me just write this down on a separate piece of paper so you can use it or screenshot. So, well, there you go. That's all you will ever be needing in terms of velocity, displacement, and acceleration. One more thing that you might want to know is let me just change this color to be yellow. One more thing that you might want to know is few formulas for angular velocity and so on. So let me just write those down too. So angular velocity is going to be 2 pi by t. Likewise, we already have discussed this. Frequency is going to be 1 over time, so we can just write 2 pi frequency, and that is all. One more thing that you have to note is here r is not going to be the length of our harmonic oscillator, but rather it's our amplitude, and sometimes it is denoted by a. Right, that is all for today, and hope you learned something. Make sure to subscribe if you want more of these types of videos, and if you have any solutions, comment it down below. Thank you so much for watching. That's all.